Hi, my name is Nina, and I'll be presenting Lab4 macroscopic views of the DC and RC circuits. An RC circuit is created when a resistor and a capacitor are connected to each other. A capacitor's voltage is proportional to the electric charge Q, and the resistor's voltage is proportional to the rate of the change of an electric charge current I. Principles tested in this lab include the energy and current conservation principles. The energy conservation principle states that the energy of interacting bodies or particles in a closed system remains constant. The conservation of current is expressed through the loop rule, which states that the sum of all potential differences across all circuit elements is equal to 0. Charge conservation is distributed by steady-state flow, meaning that as time changes, there is no change in flow, just a constant flow with respect to time. The objective of the lab is to predict the behavior of circuits containing resistors in series and parallel. This was done by using multimeters to measure actual values of conventional current and potential differences in circuits. Finally, this lab will examine the behavior of ohmic and non-ohmic resistors and capacitors. The first simple circuit consisted of two 1.5 volt batteries, two resistors, and two ammeters. Current 1 and current 2 are measured by the two ammeters reading the same value of 0.2 volts. After reversing the connection of one of the ammeters, the value still read 0.2 volts. One of the ammeters was replaced with a voltmeter and measured at the location where the ammeter was removed. Current 1, being the voltmeter, read -3 volts from the two 1.5 volt batteries, and current 2, being the only ammeter, read 0 amps. This is because the circuit was broken by the removal of the second ammeter. The break in the circuit was then replaced with a wire, and the voltmeter measured between the batteries. The voltmeter was used to measure the potential difference for each part of the path around the circuit. This was done by touching the two leads of the voltmeter to the 2 points measured. As you can see by the graph, the sum of the parts around the circuit summed to 0, holding true to the loop law. There are both positive and negative potential values around the circuit, eventually canceling out. When the voltmeter was measured across the 100 ohm resistor, the ammeter read -2.04 volts. And when the voltmeter is replaced with an ammeter in parallel with the 100 ohm resistor, the current through the other ammeter read a very high current of -1,193 amps because of the lack of a resistor. Calculations for the resistance for each of the circuit elements were calculated by the change in voltage divided by current. The resistance across the 47 ohm resistor was -0.32 ohms, -0.68 across the 100 ohm resistor, and 0 across the wire in the ammeter. In this section, we made an RC circuit consisting of a 10 ohm bulb, a 20 ohm bulb, a 9 volt battery, and a 200 megafarad capacitor. First, the battery, 10 ohm bulb, and capacitor were connected in series. The light shines very brightly, then slowly dims. The same happens when directly connecting the capacitor directly to the 10 ohm bulb. The time it took for the capacitor to charge the 10 ohm bulb was roughly 8 seconds. This process was repeated but using the 20 ohm bulb instead. The results were identical, with a brightly shining bulb slowly dimming with time. The 20 ohm bulb took about 16 seconds to discharge, which would make sense because it is double in ohm. This section consisted of a circuit with a 9 volt battery, 300 megafarad capacitor, and a 30 ohm light bulb. The voltage across the capacitor with the voltmeter was read with the red lead on the positive side of the capacitor. The capacitor was charging, and the 20 seconds worth of voltage versus time data was recorded using a stopwatch in the play-pause button of the simulator. The theoretical of this graph indicates that the discharging trend of the plot should resemble e raised to the -t over RC. The measured value of the discharge was roughly 10 seconds. Now to answer the additional questions. What if you were to do this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What difference about the real ammeter, and how would it have affected the circuits you hooked up? A real ammeter may have differed from the recorded values because only a small portion of the current is directed through the meter. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. Theoretically, the lack of a resistor would largely speed up the charge of the capacitor to a high magnitude, but in real life, it is probable that the lack of a resistor in the circuit may experience too much energy and short-circuit the capacitor with too much energy. Thank you for listening, and I appreciate your comments.